Organic light-emitting diodes, OLEDs, device architecture, emission mechanisms, materials evolution, and stability challenges. Organic light-emitting diodes, OLEDs, have emerged as a transformative technology in display and solid-state lighting owing to their high efficiency, flexibility, and superior color quality. This video presents a comprehensive overview of OLED device architecture, emission mechanisms across different generations, material design strategies, and key challenges associated with device efficiency and operational stability. Particular emphasis is placed on emissive layer engineering, exciton management, and the persistent limitations of blue emitters. Advances in phosphorescent and thermally activated delayed fluorescence, TADF, materials are discussed alongside degradation pathways and strategies for improving device lifetime. OLEDs are multi-layer thin-film optoelectronic devices composed of organic semiconductors sandwiched between two electrodes. Upon application of an external voltage, electrons and holes are injected from the cathode and anode, respectively, transported through charge transport layers, and recombine in the emissive layer, EML, to generate excitons. The radiative decay of these excitons produces electroluminescence, L. Since the first efficient OLED reported by Tang and Vanslik in 1987, the technology has evolved rapidly, culminating in commercial applications such as Sony's first OLED television, XEL1, in 2007 and flexible, foldable devices introduced by companies including Samsung, LG, and Huawei. OLEDs are now widely used in smartphones, televisions, and wearable electronics due to their lightweight nature, fast response times, and potential for flexible and transparent displays. Device architecture and working principle. A typical OLED consists of multiple nanometer scale layers, including electron injection, electron transport, emissive, hole transport, and hole injection layers. Efficient device operation requires careful alignment of energy levels and balanced charge transport properties. Within the EML, exciton formation occurs via the recombination of injected charge carriers. The efficiency of this process is governed by several factors, including charge balance, exciton confinement, and photoluminescence quantum yield, phi-PL. Host-guest systems are commonly employed, where emissive dopants are dispersed in wide bandgap host materials to suppress aggregation-induced quenching and enhance emission efficiency. The external quantum efficiency, EQE, defined as the ratio of emitted photons to injected charges, serves as a key performance metric and depends on internal quantum efficiency, IQE, and light outcoupling efficiency. Evolution of OLED generations. OLED generations are based on the type of emission mechanism that is used to emit light. The first generation of OLEDs uses fluorescent emitters. The second generation is based on phosphorescence, and the third generation relies on thermally activated delayed fluorescence, TADF, as the light-emitting pathway. The first three generations are subdivided into green, orange-red, and blue emitters, as green OLED emitters were introduced before red, and red before blue. Red, green, and blue colors are crucial for the color saturation of the OLED devices. OLED colors are defined by the L wavelength, a parameter reported for most devices. For blue OLEDs, the Commission Internationale de l'Éclairage, CIE, coordinates are as important as the wavelength for display applications. First generation OLEDs, fluorescent emitters. First generation OLEDs utilize fluorescent organic molecules, where emission occurs from singlet excitons, S1 to S0. Due to spin statistics, only 25% of generated excitons are singlets, limiting the theoretical IQE to 25% and EQE to approximately 5%. Green emitters. The first well-designed OLED device was reported by Tang and Vanslik in 1987. Early devices employed tris, 8-hydroxyquinoline aluminum, ALQ3, achieving EQEs of approximately 1% with emission around 550 nanometers. Red emitters. The first red dopant-based red OLED was introduced in 1989 by Chen and co-workers. Dicyanomethyline-based dyes, for example, DCM derivatives, enabled orange-red emission, 570 to 650 nanometers, with EQEs up to approximately 2.3%. However, aggregation-induced quenching necessitated doped systems. The introduction of assistant dopants such as rubrene improved energy transfer efficiency. Blue emitters. Anthracene-based derivatives dominate blue emission due to their wide bandgap and thermal stability. Structural modifications, such as bulky substituents to the 9 or 10 position, suppress aggregation and enable deep blue emission with improved EQEs, approximately 5%. Second-generation OLEDs, phosphorescent emitters. Second-generation OLEDs employ heavy metal complexes, for example, iridium, platinum, to harvest both singlet and triplet excitons via strong spin-orbit coupling. This enables phosphorescence from the triplet state, T1 to S0, achieving theoretical IQEs of 100%. Phosphorescent OLEDs, OLEDs, have been successfully commercialized for red and green emission, demonstrating long operational lifetimes, greater than 10 to the power of 5H at 1000 candela per square meter. However, blue phosphorescent emitters remain limited by poor stability due to long triplet lifetimes and metal-scented degradation pathways. Third-generation OLEDs, thermally activated delayed fluorescence, TADF. TADF materials provide a metal-free alternative to phosphorescent emitters. These systems feature a small singlet-triplet energy gap, delta EST, enabling reverse inter-system crossing, RISC, from T1 to S1 via thermal activation, thus harvesting triplet excitons for fluorescence. Efficient TADF requires optimization of delta EST, spin-orbit coupling, and vibronic interactions. Although TADF enables near-unity IQE, challenges include long exciton lifetimes, efficiency roll-off, and broad emission spectra due to charge transfer character. Recent developments include multi-resonant TADF, MRTADF, emitters, which combine narrow emission bandwidths with high oscillator strength, offering improved color purity for display applications. Color requirements and blue OLED challenges. OLED displays rely on red, green, and blue, RGB, emitters for full color reproduction. The emission wavelength and Commission Internationale de l'Éclairage, CIE, coordinates define color purity. For high-definition displays, blue emitters must meet stringent standards, for instance, CIE approximately equals 0.13, 0.046, for Rec. 2020. Blue OLEDs remain the most challenging due to high photon energy leading to photochemical instability, limited availability of high triplet energy host materials, efficiency-stability trade-offs. Current commercial devices often use hybrid architectures combining phosphorescent red and green emitters with fluorescent or TADF-based blue emitters. Advanced device engineering strategies. Sensitized emission, hyperfluorescence. To overcome the limitations of TADF emitters, sensitized systems decouple exciton harvesting and emission. TADF or phosphorescent sensitizers transfer energy to fluorescent emitters via forced resonance energy transfer, FRET, improving efficiency and color purity. Exciton management and charge balance. Optimizing recombination zone width and charge balance reduces exciton density, mitigating bimolecular quenching processes such as triplet-triplet annihilation, TTA, and exciton-polaron interactions. Degradation mechanisms and stability challenges. OLED degradation arises from both intrinsic and extrinsic factors. Intrinsic mechanisms, exciton-induced chemical degradation, charge accumulation and polaron-induced reactions, triplet-mediated bond dissociation, dipole reorientation and internal electric field formation. Extrinsic mechanisms, moisture and oxygen ingress, fabrication-induced defects, electrode material diffusion, such as indium from ITO. Blue emitters are particularly susceptible due to high-energy excitons that accelerate bond cleavage and photochemical reactions. Thermal effects also play a critical role. Elevated temperatures can induce morphological changes, e.g., glass transition, and accelerate degradation kinetics. Device lifetime and standardization. Device lifetime is commonly quantified using metrics such as LT50 or LT95. For commercial viability, OLEDs must achieve LT95 greater than 5000 H at 1000 candela per square meter. However, the lack of standardized testing protocols complicates comparisons across studies. Borrowing methodologies from organic photovoltaics, for example, ISOS protocols, has been proposed to improve reproducibility and benchmarking. In conclusion, OLED technology has undergone significant advancements, transitioning from low-efficiency fluorescent systems to highly efficient phosphorescent and TADF-based devices. Despite these developments, achieving stable, high-efficiency blue emission remains the principal challenge. Future progress will depend on the rational design of emissive materials, improved device architectures, and a deeper understanding of degradation mechanisms. The integration of advanced emitter systems such as MRTADF and hyperfluorescence, combined with optimized charge transport and encapsulation strategies, is expected to drive the next generation of high-performance OLEDs.